So we're going to look at more detail at the pressure changes in the heart. And when we do this, we're going to look at the left ventricle, the left side of the heart, only as an example. So before we do that, I want to let you know the pressure differences in the two circuits. So we've got two pumps, right? The circulatory system is made up of the heart with two sets of pumps. This is our systemic circulation over here. And this needs a pretty good pump to force blood through this entire system, the entire body, up to your head, going against gravity. This is a high pressure system. This pump is going to generate a very high pressure in order to get that blood to flow throughout the whole body. So we'll look at this again. You may have heard these numbers. So in the ventricle here, the left ventricle, pressure is 120 millimeters of mercury when it's contracting, and goes down to like 10 when it's relaxing. At the aorta, this is where we measure blood pressure. So there is about 120 over 80. And that's where you measure blood pressure. You don't, actually not at the aorta, it's at your brachial artery, but that is basically the same as your aorta. High pressure, and that's going to allow blood to flow through the entire circuit. So pressure is going to allow for flow. And we'll come back to that idea when we get back to the vessels. The right atrium and right ventricle do not generate the same pressures. So the right ventricle, this is our low pressure side, our low pressure circuit, because that's pulmonary, high pressure is systemic. We don't need to generate the same amount of the same pressure. We're not going very far. The blood's not going very far. It's going to the lungs and back. So it's not going to generate that same pressure. It's going to be about 25 millimeters of mercury at a contraction, so in systole, and go down to about 4 millimeters of mercury. So quite a bit lower. Even though the same blood is going through there, you don't need to squeeze quite as hard. You don't need to generate the same pressure to have flow through the entire circuit. So the Wiggers diagram is a graph of the cardiac cycle. The pressure changes over time, and it's meant to be helpful to understand how changes in pressure correspond to each of the events, but it does require looking closely at it. It's kind of like the estrus cycle events. There's a lot shown there. So I'm going to draw it, and then we're going to look at another picture of it as well. What it's doing is it's really a diagram of the left side of the heart we're going to use as an example. So the pressures in the left side are slightly greater than the right side because the left side of the heart has to pump to the entire body. So that's what we're going to graph here, like the left ventricle. And that's what, So what I have shown here so far is pressure in millimeters of mercury over time. And I've got some numbers here from 0 to 120. Millimeters of mercury is a measure of pressure. So barometer that measures air pressure would also measure millimeters of mercury. Up top, I've got the phases of the cardiac cycle that we've already talked about and kind of color coded. So what I want to start with is looking at ventricular pressure, which we did in the previous video already. So I'm going to make this purple to correspond to the ventricle. Ventricular pressure is going to start pretty darn low. I'm going to go right here. And it's going to have a little blip here that corresponds to atrial systole. When the atria contract and kick that little bit of blood, that 20% into the ventricles, pressure is going to increase some. But then really the most important thing is this huge increase due to isovolumic contraction, followed by a sharp drop due to ventricular ejection. So during ventricular systole, we've got a sharp rise in pressure and then a sharp decrease in the left ventricle. Right ventricle as well, but not to the same extent, not the 120. This is going to drop then, and then kind of slowly start to rise back up as the ventricle, actually I'm going to drop it down a little bit lower to be consistent with what I started with. And then it's going to rise back up as passive filling occurs, a slow rise. So this is the left ventricle. Let's go to the aorta next, because that's physically connected to the left ventricle. So those changes are going to correspond to ventricle. They're all going to correspond, but these ones kind of directly. Aortic pressure is never going to be as low as the pressure in the heart. So the low end in the aorta is about 80. 120/80 is average blood pressure in the aorta, which is the same as the blood pressure measured in your brachial artery that we'll come back to next week. So this is aorta. We're going to have a kind of a slow decrease here, and then we're going to have it kind of follow along the ventricular pressure. It's going to drop. It's going to be a little notch here, and then it's going to go down. This is aorta. So following kind of along the ventricular pressure, because the aorta is receiving blood from that left ventricle. This here is called the dicrotic notch. It's due to backflow after the semilunar valves close. The aortic valve is going to close. Aortic valve is going to open right here. That causes a slight decrease in pressure as you relieve pressure right as the blood flow increases. And then you're going to have a slight increase here as a consequence of that valve closing again and increasing pressure very transiently in that local aorta before the blood flows away to the heart. To the body, sorry. Okay. So then lastly, we've got atrial pressures. Atrial pressure is going to also be pretty low at rest. Atrial diastole is what we're at right now. During atrial systole, we've got a bump up as that heart contracts. And then we're going to kind of stay low before we rise back up during atrial filling. So this is when there's that filling of the ventricles that goes through the atria. So kind of we've got some fluctuations through here. You can see right here I have systole again. That's where that contraction is increasing it right here. So kind of the key point right here is that during atrial systole, we do have a small increase in pressure that then goes back down as that blood goes to the ventricles. So another image of the Wiggers diagram showing these changes in pressure over time throughout the cardiac cycle. So in the left ventricle, left atrium, and aorta, similar changes would be seen in the right side, but the pressure wouldn't reach quite such a high level because the right side of the heart does not need to pump to the whole systemic circulation. It's just pumping nearby to the lungs. So the same volumes would be pumped, but not at the same pressures. Pressure is going to allow for increased flow. The other thing that's on this image that wasn't on the previous one I drew is the EKG. So here are the components of the EKG that you know about that correspond to these to contraction events, which correspond to pressure events. So the P wave is atrial depolarization. It's going to cause atrial contraction, and that's going to cause an increase in pressure in the atria. So you might imagine we could look at what happens to blood flow, which we already have talked about, with these changes in pressure, right? That's why we care about pressure. Pressure is going to cause flow. And we'll look at more of the physics of this with both respiratory and blood pressure. But if we want to have flow happen, we have to have a pressure. If we have a pressure change, the point of this is to have blood flow. And you already know that, right? You know that this is going to be ventricular ejection happening right here. Let's look at that. So this graph here is, this image is ventricular volume. Pretty simple and it makes sense. We've got an increase in ventricular volume as we have filling of the ventricles, passive filling, and then atrial systole to top it off. Then we've got a dramatic decrease in ventricular volume as we have that ventricular ejection. Do note here that the increase in pressure continues beyond when the blood flow starts exiting. There's a delay in the consequence of blood flow on pressure. So this is a dramatic increase in pressure that's going to cause ventricular ejection. Pressure blips over a bit, even though blood flow has already begun going out. So just note that to help it make sense. These changes in volume, which you also can see down here, we've looked at these already, have names. So we've got something called a stroke volume. This is probably the most important one. We'll use it the most. Stroke volume is the amount of blood that's ejected during that stroke, during that contraction. And it's not equal to exactly to the blood that we started with. It's going to be equal to that blood we start with minus the blood remaining in the heart. The heart doesn't pump out every single drop of blood. So there's of course names for these too. The end diastolic volume is the amount of blood that is the maximum, is what we're starting with before that contraction. So after passive filling and then atrial contraction, the ventricle is full of blood, end diastolic volume. What's left after contraction is called the end systolic volume after contraction. And that is a lot less, but it's not zero. So because it's not zero, the stroke volume is not the same as what we started with.